Hey, welcome students. So today I thought to bring to you the topic of for class 11. So it will be a demo class of maybe half an hour or so. And we will discuss one important topic for class 11, which is uniform circular motion. And obviously, since it's a demo class, I will not be able to delve into too much of the details. Obviously, before understanding uniform motion, uniform circular motion, we should be knowing how to, we should be well aware about vectors and, we should be also aware about some laws of motion and some uh, kinematics, right? So, I am hoping that you are already aware about that, and then I'm just bringing the demo class for uniform circular motion. So we'll talk around that, and wherever possible, I will try to explain in as much depth as I can. And also towards the end, we will look into one or two problems to support our theory. So first of all, welcome to EdFalco Academy, an epitome of Faro education, which means faster, accurate, affordable, and result-oriented education. And myself, Nishant, from IIT Madras, and having 14 years of industrial experience and also 7 years of teaching experience. So hope you will enjoy this lecture or video, and hoping that it will add some value in your studies. And in case if you have any further questions, queries, any doubts, you can definitely get back to us at any point in time. You can call us at our number, or you can email us, or you can visit our website. We have online, offline, online courses, online classes, and offline classes, test series, everything available there. So you can take leverage of that. And with that, so let's start this chapter without much ado, and uh, take pen, copy, whatever you want to take, and let's see how what this chapter is all about. Okay, so now we will start this chapter, uniform circular motion. Uniform circular motion. So there are three words associated here, right? One is uniform, one is circular, one is motion. So why do we call, obviously circular is, it's very clear that circular basically means the body is going in a circle, right? The body is going in a circle. And motion, is nothing but the change in the position, right? So obviously when the body is moving in a circle, its position is changing. So the word circular is depicting that it's in circle. Motion means that its position is changing every time. So circular motion is fine. But what is this word uniform, right? Why we are calling it uniform? So uniform basically means that there is some parameter which is not changing. It is constant. In case of circular motion that we are studying, what is that parameter that we are calling it to be uniform, or which is constant or not changing? So the velocity is that parameter which does not change. Velocity is constant, right? Velocity is something that we are calling as constant in a circular motion. So with that understanding, now we are clear. We are talking about a motion in a circle which has a uniform velocity. Now, this circular motion can happen in any plane, right? It can happen in, let's say, a vertical plane like this, or it can happen in a horizontal plane like this. This is also circular motion in a horizontal plane, or it can happen in any other plane as well, right? It can happen in any other plane as well. Suppose this is my plane. So, and the circular motion is happening like this. Same way, if suppose this is my horizontal plane, the circular motion is happening like this, or it can be a vertical plane as we have seen. So, with this understanding, now let's move on to understand certain parameters and how we can actually define the uniform circular motion. So, as we mentioned that first of all, a circular motion, since it's a circular motion, let's start by drawing a circle. So here is the circle. The body that we are talking about is, let's say this is the body that is moving in this circular path, and it has, let's say, mass m, right? And this is the center of the circle. Let's call it O as the center of the circle. Now the velocity or the displacement uh, per unit time, right? That's what we define the velocity as. That is tangential to the point at which we are talking about. So if suppose we are talking about this point A, the velocity is basically tangential at this particular point. Now, when I say velocity, it is a vector, right? Velocity is a vector quantity, is vector. Now, when I said velocity is constant, I actually meant that the magnitude of the velocity is constant. Magnitude of velocity is constant in this uniform circular motion. The direction of this velocity is not constant, it's changing. So as I said that at any point the velocity is vector is going to be tangential, and let's say its magnitude is v, then at this point also it is tangential, but its magnitude is just v. At this point also it is going to be tangential, magnitude is v, or any other point for that matter. The value is v, but the direction, as you can see, it is always changing. Here the direction is in this direction. Here the direction has changed to another direction. Same way at each point. In fact, at each point, you will see that the direction is different, right? At each point, it will be tangential, and the direction you can see will be changing at each of these points, right? So the magnitude of the velocity, which we call as speed, that is something which is constant, okay? But the direction is not constant. Direction of velocity vector is not constant, is changing, changes, right? It changes. So having understood this, and also that the fact that the velocity magnitude, which is a speed, is basically constant, but direction is not constant. And we also know that the direction is tangential to the point that we are talking about. But let's see why the value of, or the why the direction will be tangential. So to understand that, let's say we have this circle in which the motion is happening, and let's say this is the center, this is the radius. The body was earlier here at point A, the center is O, and then let's say it has moved to another point B, right? So it has moved from point A to point B on this circle. Now, if you try to see what the displacement is, the displacement of the body is nothing but the straight line joining A to B, right? The straight line that joins A to B is the displacement. A, B is nothing but my displacement. Is nothing but the displacement, right? And obviously let's say that the radius of this circle is r. So AB is my displacement. And what is the definition of velocity? Velocity is basically, or the velocity vector is nothing but the rate of change of displacement. So that means ds vector by dt vector. Dt, sorry, not dt is not a vector, dt is a scalar quantity. So it is ds vector by dt. Now, uh, the velocity vector is defined as the rate of change of displacement. Okay, so the direction of displacement change, the direction of displacement change or displacement, right? The direction of displacement will be same as the direction of velocity, right? Direction of velocity. So the direction of displacement is nothing but same as the direction of the velocity. So you can say directly that this is the direction of velocity, right? Because the direction of displacement is along the line AB. Therefore, the velocity will also be along the line AB. But just now I said that it is tangential. Now this line AB is not tangential, as you can see, right? So the line AB is like what? If suppose you have a circle, it's a line joining the 2 points. What is this line called? The line is basically called as secant, right? Which makes basically the chord of the circle. It is a secant. It is not tangent, right? Tangent means it is just touching the point, touching the circle at one point, right? This line is the tangent line. The another line is called the secant line, which actually forms the chord of the circle. So right now, whatever the AB line that you see, which represents the displacement, It is basically the secant line or the chord. It is not the tangent. So how come the velocity is tangent? So the point here is that we are talking about a very, very small displacement. In so the velocity vector, as I said, is equal to ds vector by dt. So so in a very differential format, we call that, let's say there is a very, very small change in the displacement, which we are representing as ds vector, and and in a very small amount of time dt, right? So why we take this approach of ds by dt? Why don't we take simply s by t? Because it might be possible that the velocity vector is changing every time, right? Or if there either because of the change in the magnitude or because of the change in the direction or combination of both. If the vector of the velocity is changing at each point in time, right? Then taking the differential approach to define velocity vector is more appropriate, because then you are talking about a very small time, and then you are just saying that at that particular point in time, if there is a small movement of ds vector, that is the displacement, if small displacement is happening in that small time, then that will be the velocity at that particular point, or that will be the velocity at that particular point in time, right? And if the moment I talk about a different time point, that ds by dt will again might be different, right? So that's why we take a very, very small distance and a very, very small time in order to define if the things are changing over the time, right? If it is very, very uniform, right? If it is completely uniform, if it is like the velocity vector is not changing at all, right? Neither the magnitude is changing nor the direction is changing, right? It is constant, completely constant. So in that case, whether you take ds by dt or whether you take a bigger s divided by a bigger t, it doesn't matter. So in that case, ds by dt is approximately similar to your s by t. But as far as this case is concerned, here we are seeing that the velocity vector is indeed changing at each and every point, right? So it makes sense to take ds by dt in order to define velocity. So that's what we have taken. So velocity vector is nothing but ds by dt vector, and the direction of a ds vector is going to define the direction of v vector as well. So here, since ds is in this direction, right? And if I take AB to be very, very small, right? AB was the ds vector, right? AB is nothing but describing the displacement, which is my ds vector. And if I take this AB to a very small value, right? Which means I take ds to be tending to zero, right? Tending to zero. I said tending to zero, not exactly zero, because if it becomes zero, then we cannot define velocity, right? So it cannot be exactly zero, but a number which is very, very close to zero, infinitesimally small, right? We call it. So in that case, the point B will become so close to A that this line AB will actually collapse at the point A, right? So what I mean to say is that in a circle, suppose A point is here, B point is here. If this is the chord which was being made, if I start moving the point B very, very close to A, what you see is that ultimately a time will come when it will be so close that it will be just a line over here itself. It will become a tangent line, right? And that is what is happening with this definition of ds by dt vector. When we are taking a very small displacement over a very small period of time, then my velocity vector is is becoming actually a tangent at the point A. And that is the reason why we say that velocity in a circular motion, the velocity vector in a circular motion is always tangential to the direction, tangential to the point which we are talking about. So at any point, if we take the velocity vector is pointed towards the tangent direction. The value of this velocity vector, which is the speed, right? That or the magnitude of this velocity vector, which is speed, is always same. So everywhere the value is v, but but the direction is changing. um, uh, it's always changing, right? It's always changing throughout the motion in the circle. The direction is changing. So that's one thing about velocity and its direction, that why it is tangential to the at any particular point. Now another important parameter to understand is about there is another important variable that we should understand, which is called angular velocity. Angular velocity. So far, you have studied about that if the body is doing some displacement over a certain period of time, then we call it as velocity, right? That is called as velocity. You can also call it translational velocity because it is moving in a translatory fashion, or it is moving in a linear line, right? It's moving in a line. So you can call it linear velocity, you can call it translational velocity, or simply velocity. Here we are defining a new variable which is called as the angular velocity. So what does that mean? So when we are talking about any displacement, let's say from point A to point B, right? We can there are two ways we can think about it. One is the way that we just thought about it, where we talked like AB is the displacement, right? From A to B, the displacement is happening, right? The same thing we can talk about in terms of theta also. Suppose that this AB chord is extending an angle of theta at the center, right? So then it has done a angular displacement, or angular position has changed by an angle of theta. So the angular displacement is theta, basically theta angles, right? Theta radians is the displacement in the angle that has happened from the point A to B, right? In that sense, if we try to define uh, uh, the angular velocity, we can call angular velocity, which is represented by omega, as equal to d theta by dt. So when it was displacement, we were calling it the displacement, the rate of change of displacement as velocity. The rate of change of angle is called as angular velocity, right? And again, angular velocity is also a vector quantity, right? It's also a vector quantity. So that is like we will talk about it later about what is the angle of this omega. Omega is basically in the, if your theta is changing like this, your if you curl your hand in the direction of theta change, the thumb will point in the direction of your angular velocity. So we'll discuss that in more detail, but for timing, let's understand about the magnitude at least of the angular velocity. The magnitude of the angular velocity can obviously be magnitude. This represents magnitude of angular velocity is nothing but d theta by dt. So that is one important variable which we have defined when we are studying uniform circular motion, angular velocity. Now, the same thing why I have, and one more thing why I have taken d theta. It again the same thing. Like if I start making this point A to B as very small, if I make A to be very small so that I get ds by dt, on the angle terms, my theta will become very small. Theta will become very small. So in that case, it will become d theta, right? Small angle change. So, so that is what is it is. It is describing the angular velocity. So now let's move on to find the relation between V and omega. What is the relation that exists between V and omega? So in order to derive this relation, we already know that V is nothing but ds by dt. Now let's concentrate on this circle which has gone from point, the body has moved from point A to B on this circle, and it's in terms of angle, it has traversed theta angle. Okay, so in this case, the displacement ds is nothing but AB, right? And it has happened in, let's say, small time dt, right? Small time dt. Imagine, we will imagine that A and B are very close. A and B are very close. So therefore, the displacement is very small. It is ds, right? And obviously, in that case, d theta is if this quantity A to B is ds, which means it is very small, then theta is also very small. It can be written as d theta, right? So in that case, Now, before we move on to describe the relation, we should understand one thing, that in a circle, if you have an arc, right? If you have an arc which is subtending an angle of theta, right? Which is subtending an angle of theta, then this arc length and the radius of the circle is, let's say, r, then the value of this arc, the length of this arc, becomes equal to theta into r. Now, how does that happen? Many of you might be already aware, but for understanding purpose, I will just brief about why it is. So it is basically based on the definition of radians. So by the way, this theta has to be in radians. Theta in radians. Theta should be taken in radians. Then only we are utilizing theta into r as the. Then only we are calling theta into r as the length of this arc. Theta has to be in radians. So why it is so basically that it is coming out from the definition of 1 radian. What is 1 radian? How do we define 1 radian? 1 radian is the distance. So on a circle of radius, let's say r, if you make an arc which is also of distance of length r, so this arc is of length r, right? And this the circle radius is also r. So in that case, if both of them are r, then the angle that is subtended is nothing but 1 radian. That is what the definition of 1 radian. So 1 radian is the angle that an arc of length equal to the radius of circle subtends at the center, right? So that is the definition of your 1 radian. Now with this understanding, you can very well see, you can very well see that if there is a circle which is having 1 radian, that means it is this length is equal to r, right? If its radius is r, this length is r. Now imagine if it is theta angle, the angle is, let's say, theta, then by simple unitary method, you can simply say that this will become equal to theta into r. This would become equal to theta times of r. Because for 1 radian, you are getting r distance. For theta radians, you are going to get theta r distance of arc, right? Of this arc. So that is why when theta is in radians, this distance is nothing but equal to theta r. And guess what? You already know this, but just I'm pointing out here that if suppose if the theta if the theta if theta becomes equal to 2 pi radians, right? If it becomes equal to 2 pi radians, then what happens? So in 1 radian, you are covering r distance, right? In 1 radian, you are covering r distance. If this is 1 radian, that means here you are covering a distance of r, right? If it will be 2 pi radians, how much distance on the circle you will cover? You will cover 2 pi r distance, and you all know 2 pi r represents the entire circle, right? So the entire 2 pi r length of the arc will be covered, or the entire circle will be covered, if you are taking 2 pi radians. 2 pi radians. In terms of degree, if you see, this entire angle is nothing but 360 degree, and that's why we have this relation that 2 pi radian is equal to 360 degree, right? Or pi radian is equal to 180 degree. So this is the just like the definition of radian, and because of that only we are getting that if the angle subtended is theta radians, then my length of the arc is nothing but theta r. So we will try to utilize this in order to find some relation between v and omega, because that's what our primary purpose was, right? So okay, so now we know that v is equal to ds by dt, right, in the scalar format, right? Ds by dt. Um, so if we take the circle now, right, and let's say the body has traversed a distance of ds, right, ds, and the angle here is d theta, right, in the small amount of time dt. So we just talked about that ds is equal to r d theta. Now here one thing to understand is this ds was is basically this line. When I was talking about this circumference, right? This arc length, right? But the point here is that this d theta is so small, right? That the ds value or the length value of the secant is approximated to the value of the curve. So what it means is like if you are drawing a circle and if you're taking this point and a very near about point to it, right? So if you draw a straight line, right, that is ds, right? But if you want to take the actual rate actual on the periphery of the circle, or you want to take the arc actually, the length basically becomes length basically becomes same. So the ds length is nothing but the length of this arc itself when theta is very small, right? So that's why we are approximating that this particular arc length is nothing but rd theta. So we can call it that, okay, yeah, ds is also because d theta is very small, ds is also similar to that arc length. So let's call that, okay, ds itself is equal to rd theta. Okay, so that's one thing. Now, since we know that v is equal to ds by d theta, I can write this. I can write it is equal to d of r ds by d theta. So, I can write. Sorry, just a moment. ds can be written as r d theta. ds can be written as r d theta. So I have converted it to r d theta instead of ds by dt, right? So this is r into d theta by dt. Now this d theta by dt quantity you already saw in the previous case, that we had defined the angular velocity to be equal to d theta by dt here, right? This is the quantity, angular position change with respect to time. That is what is your magnitude of omega. So therefore, using that, I can now very well say that this is nothing but equal to r into omega, right? So V is equal to r into omega. V is equal to r into omega, right? This is the relation that exists between velocity and the omega. Obviously, this is a simple scalar equation, right? So we just multiply omega with r and we get the velocity. But we know that all these terms like the radius, the omega, and the velocity, all of these three terms are actually vectors, right? The radius is also a length vector, or it is a length vector basically. Omega is also a vector. Velocity anyway is a vector. So what is the direction of omega? So the direction of omega will be more clear when we talk about the vectorial representations of all these equations somewhere later in the chapter. But for now, at least I can explain you, as I was telling earlier also, that if suppose the body is moving in having the velocity v and is moving like this, right? So if it is going in a plane all around like this, you curl your finger towards the motion of the velocity. So the velocity is all like this, right? So you curl your finger in the direction of velocity. The thumb is going to point in the direction of omega, right? So omega will be pointing perpendicular to the plane of motion, right? So if suppose the plane of your circular motion is this, velocities are going to point like this, right, tangential at each point, and the omega will be in the direction which is perpendicular to this plane, right, in the upward direction, omega, right? This is the perpendicular direction, perpendicular to this plane, right? So that is the direction of omega. So obviously, I think it will be easier to calculate all this when we talk about the vector representations of all these quantities, and when we discuss about cross product and dot products, etc., which will give more clarity into how to determine the omega direction. But for now, in the case of uniform circular motion, the omega is pretty much a constant value, is a constant value. because the velocity vector, although it is changing, right? Velocity vector, although it is changing, it is tangent to each of the points that at each point wherever we are talking about. But the value of omega, which is the magnitude is r into omega. R is a constant because it's a constant radius circle. Omega and velocity is also, the magnitude of velocity is also constant. So omega, which is equal to v divided by r, is also going to be constant. And magnitude wise also, if you look at it, its magnitude is always pointing in the upward direction, right? So magnitude wise also it is constant, and value wise also, the direction wise also it is constant. So both direction and magnitude is constant for omega. So omega is indeed uniform, right? Omega is also one important quantity which is uniform in this circular motion. It is actually more, you can say, in case of velocity, it was just the magnitude which was constant, but in case of omega, it is actually both which is constant. It is the direction also which is constant, it is the magnitude also which is constant, which is equal to v by r, the magnitude of v divided by the radius of the circle, which is also constant. So omega has both these things constant. So it's indeed a constant vector in the case of uniform circular motion. And more on this we will study, as I said, when we study the vectorial representation of the equations. Now, another thing that we need to study in this circular motion is about, now you understand that the velocity vector is changing because the magnitude of velocity is always changing, right? Although the magnitude of the velocity is constant, but its direction is always changing. Sorry, the direction is always changing. The magnitude is constant. Now, in case of vector, if there is either the change of magnitude or the change of direction, the acceleration will happen because acceleration vector is equal to the rate of change of velocity vector. So acceleration vector is equal to dv vector by dt. So if the velocity vector is changing either because of the change in direction or because of change in magnitude or combination of both, acceleration is going to be present. So let us try to find out next that what this acceleration is in the case of a uniform circular motion. So in order to derive that, let's take a circle first, and you already know that the velocity vector, if suppose it is at the point A, the velocity vector is going to point like this, right? And suppose the body moves after a time dt to point B, then the velocity vector will be acting again like this, right? And let's say the angle changes, the angle is changing by d theta, right? So now, so we have to find that what is the, as you have seen that the acceleration is nothing but the change in the velocity vector. So let us construct the change in the velocity vector. How much is the change happening? So the initial velocity vector, which is, let's say, vi, right? This is the initial velocity vector. Let me draw initial velocity vector, which is vi, and the final velocity vector is this. Final velocity vector is this, right? Suppose this is my final velocity vector, which is nothing but this vf vector, right? This is vi vector. Okay. So, and obviously the value has changed by an angle of theta. So this angle that you are seeing over here, from the velocity vector has changed from this, I mean, being uh, at an angle which is horizontal, which is vertical, by an angle of theta it has changed, right? Angle of d theta it has changed. So this angle that you see is nothing but d theta. It has changed by an angle of d theta. So this is how the picture would look like, right? If you draw it. And if you want to find out delta v vector, which means the change in the velocity vector, it is nothing but final velocity vector minus initial velocity vector, right? So change is nothing but final minus initial. So in this case, this is my VF, VI. I just want to draw V minus of VI, right? So the minus of VI will be something like this, right? It will start pointing in this direction. This will be minus VI. Now I simply need to add VF and minus VI to get VF minus VI, right? So what I will do is I'm simply going to add this VF and I'm going to add VI. So this is nothing but my VF and this is nothing but my VI. So I'm just taking help of the parallelogram law of addition. So while studying this chapter, as I had already said that you will need the understanding of vectors and all. So for now, I'm assuming that you have an understanding of vectors. If not, when we are doing the actual classes or when we are trying to understand, definitely we will first be looking at what the vector is or what are the various mathematics involved with vector, how to resolve the vectors, etc., how to do their addition, multiplications, and finding the products of vector, etc., etc. All those topics we will discuss first, and then we will move on to this particular topic so that it becomes more clear. But for now, I am just assuming that that topic is clear to you, and I'm just discussing the uniform circular motion. So now in this case, the you can see that the value of your Vf minus Vi will be this vector, right? It will be this will describe your delta V vector, right? This direction. Now imagine this is the picture how it will look like, right? This is how the vectors will look like. Now just concentrate on this angle d theta, right? This angle d theta. Although I have drawn it as a high value of angle, as you can see that obviously this is not d theta, right? This is a bigger angle that I have drawn. But imagine in your mind, or just give an imagination that if this d theta is very small, if this d theta is small, very small, what is going to happen? You can see that this vector will move in this direction, right? It will go somewhere here, right? It will go somewhere here at a very small angle, right? At a very small angle d theta. And what will happen to this vector in that case? You can see that this vector will also move in the upward direction, right? Till a point, if d theta is very small, what you will see is that this vector is almost like this, almost like a horizontal line, right? So if so you can see that if this is the tangent line, if B is very close to A, right? If B becomes very close to A, the change that is going to happen, right, will be will be very close to the radial line, right? The change will be very close to. So suppose if it is this, if it is this, then the change that is happening is how much? You can see here that let me draw it properly again so that it is clear. Suppose this is my circular motion path, and and this is one point, and there is another point which is lying very close to it, right? So this is point A, this is point B. This one is in this direction. This one is in this direction, right? And as I said, if you have to find delta V, that is nothing but VF minus VI. This is your VI, this is your VF, right? So the magnitudes are same, right? The magnitudes are same. So you can draw here minus VI, right? Minus vi will be just opposite of vi, and then if you try to draw the resultant, it will become very close to like this. And the more and more this b becomes close to A, you can say that at a point, if B is so close to A that it is that point A itself, then this particular line that you are seeing, this particular delta V vector that you are seeing, will almost become the radial line, will almost become the radial line. So the acceleration vector direction of acceleration vector, direction of acceleration vector is towards the radial line, towards the radial line, pointing inward, right? Pointing inward. So, so far what we have seen is that if suppose there is a circular motion, uh, the body at any particular point, at any particular point, at any particular point, the body will have a velocity which will be tangential to that point A, right? And its acceleration will be in the radial direction pointing towards the center, right? And couple of things about this. It is now it's now clear that okay, it will be pointing towards the radial, but what is the physical meaning of this? So you can see if suppose this body is there, right? This body is there. If it has a velocity in this direction, what is going to happen? The body will simply try to move in this straight line, right? Because its velocity is in that direction, so it is going to move in that direction. But every time, right? Every small time, it is getting pulled towards the center. It is getting pulled towards the center. The moment it tries to move here, it is getting pulled to the center. The moment, so it takes a small turn, right, in the circle direction. Again, here its velocity is tangent. It tries to go in this direction, but as it moves slightly away, it is again being pulled towards the center. So at each point, it is being pulled towards the center, right? And that is the reason it is being kept in the circular motion. So any point it tries to move in the tangential direction, the moment it moves a little bit, right, a little small amount in time, very, very small amount in time, it gets pulled down towards the center. And that is how at each point, since it is getting pulled towards the center, the motion is happening in a circular fashion. And now, since it is getting pulled towards the center each time, right? So that means that there must be some force which is trying to pull it towards the center. There must be some force acting, and that force must be in the radial inward direction, right? That force must be in the radial inward direction. And this is the force that we call as centripetal force, right? This is the force we call as centripetal force. This is the force which is actually trying to, at each point in time, at each point, it is trying to pull the body or the point mass towards the center, right, as it tries to move out in the tangent. So now, since there is a centripetal force, there is a force which is pulling it at the center. The acceleration, according to Newton's law, we know F is nothing but mass into acceleration. So if the force is acting in the inward direction towards the center at each point, right, that means the acceleration also must be acting in that same direction, because the force vector is equal to mass into acceleration vector. So the direction of the force is also the same as direction of the acceleration, right? So far we have understood that the velocity vector is always pointed in the tangential direction and the acceleration vector is pointed in the radial direction. And that means that we already know that a tangent and the radial line are always perpendicular to each other. Therefore, the velocity and uh, the acceleration must be perpendicular to each other in case of uniform circular motion. So now we have understood the direction of acceleration. The next important thing to understand is what is the magnitude of this acceleration. So in order to understand the magnitude, let's again draw a simple circle, right? And now suppose you have a velocity v, which is initial velocity vi, let's call it vi, and after certain point in time, let's say the velocity is in this direction, in the tangential direction again, which is vf, right? And let's say that in this time from the center, the body is basically covering an angle of theta. That means the angular change is basically theta degrees, right? This is theta, not degrees, theta radians, theta radians. So now how do we find acceleration? You already know that the change in the velocity vector divided by delta t is equal to nothing but your acceleration vector, right? So the acceleration vector must be in the direction of the change in the velocity vector, and the rate of the change of velocity vector is nothing but acceleration. So if we go and in case if we try to make this difference very small, that means if we try to take limit as delta t tends to 0, right, in a very small interval of time, then dv delta v vector will become basically dv vector by dt. So dv vector by dt is nothing but your acceleration vector, right? So it will basically you are applying this limit of delta t tend to 0 on this expression, right? So you are saying limit delta t tend to 0, delta v vector by delta t is nothing but dv by dt, d vector by dt. So that means this will become your acceleration. This is what is your acceleration, right? So now it is clear that I have, if I understand or if I am able to find what is the change in the velocity vector, then I should be able to find what is the direction, as well as direction anyway we just understood. We will be able to tell what is the magnitude of this acceleration. So in order to find that, let's draw it in one place first. So this is my vi vector, and this is my, let's say, vf vector, right? And this angle is basically theta, right? So if I have to calculate vf minus vi, I can make actually opposite of vi. So instead of this vi, I will make this one, which is minus of vi, right? Just in the opposite direction. And then the resultant of these two, which means vf plus minus of vi, will be nothing but vf minus vi, or it will be similar to your delta v. So I will just do the parallelogram law of addition, and this vector over here is nothing but my vf minus vi. So that is representing my delta v vector, right? Also, you know that if any two vectors are there, let's say a vector and b vector are there. So how do we find a vector minus b vector? A vector minus b vector, magnitude of a vector minus b vector. It is nothing but root over magnitude of a square plus magnitude of b square plus, sorry, if it is plus, then it will become minus. If it is plus, then it will be, if it is if you are doing subtraction, then you will be doing subtraction. So it will be minus 2a vector b vector cos theta. Theta represents the angle between the two vectors basically, right? So cos of theta, because the angle between the vi vector or and the vf vector is nothing but it is coming out to be theta degrees. So it is mod a square plus mod b square minus 2 mod a mod b cos theta. So now applying the same thing here, the v final vector minus v initial vector mod, which will give me the mod of delta v vector basically, will be equal to root over mod of b vector. We know, let's call it v square, right? Same way the another vf is v square, vi is also v square minus 2 into v cos theta, right? So this is what it will be, which can be further written as 2v square into 1 minus cos theta. Now, if you have studied trigonometry, or if you have to study in later point in time, you would come across a formula which says cos of a plus b angle is equal to cos of a plus a cos of a cos b minus sin a sin b, right? So that means if I put a is equal to b, I can say this is cos 2a, this is equal to cos square a, which means cos a into cos a minus sin square a, right? So the moment I do this, I can now put it as cos square a. You already know it is nothing but 1 minus sin square a, right? By the identity that cos square a plus sin square a is equal to 1. Using that, I have converted cos square A as 1 minus sine square A minus sine square A, which makes it 1 minus 2 sine square A, right? Or you could have also written it in terms of cos square A, which means you could have written the same thing into, just keep cos square A, and sine square A you can make it as 1 minus cos square A, 1 minus cos square A, right? After opening the bracket, it will become cos square A plus minus 1 plus cos square A, which makes it 2 cos square A minus 1, right? So here now we see this is 1, this is 1 minus 2 sine square, 1 minus 2 sine square, right? Okay, so if you look at this one, cos 2a is equal to 1 minus 2 sine square a. From there you can directly say 1 minus cos 2a is nothing but 2 sine square a, right? Is nothing but 2 sine square a. So if I substitute this same thing over here in 1 minus cos theta, I'm going to get basically root over of 2v square into 2 sine square theta by 2, right? 2 sine square theta by 2. So taking this down, taking it this side, let's calculate it. Let's little bit simplify it. So we got this is equal to your magnitude of delta V, right? Which is equal to 2v square into 2 sine theta by 2 from our identity that we just talked about. So now in this case, one more important thing. Since as we are talking about finding the acceleration, the delta v that we are trying to find, we are trying to find the small change in the velocity in a very, very small duration of time. In that case, the change in the angle, right? The change in the angle. So in a circle, we are trying to find the change in the velocity for a very, very small time, right? It's such a small time that another point lies just near to the original point. So A, B are very close. A and B are close, very close, right? So that means the angle that it will subtend at the center, this angle d theta, is going to be very, very small, right? Or theta is going to be very, very small. Now, in that case, you already know that if limit theta tend to 0, sine theta is approximately equal to theta. Now, when we study limits and when we study calculus, we will and limit chapter, then you will understand why it is. But for time being, at least you can think of that the sine theta function will be almost equal to theta if theta is very, very small, or it is limit of theta tending to 0. So with this thing in mind, since it is approximately theta, we can write this delta v as, or dv now, dv vector magnitude, because you have already taken theta as very, very small, can be written as root under of 2v square, 2v square into 2 theta by 2, theta by 2 whole square, theta by 2 whole square, because it was sine square theta by sine theta by 2, which can be converted into approximately theta by 2. Sorry, it was 2 sine square theta by 2, 2 sine square theta by 2, because the formulation was 1 minus cos, 1 minus cos 2a is equal to 2 sine square a, right? So based on that, 1 minus cos 2 that cos 2 theta got converted into 2 sine square theta by 2. So that is what you have put here. So it will be, instead of sine square theta by 2, now you are assuming that theta is very, very small, so it will be theta by 2 whole square, right? So now this can be converted into root under 2v square into 2 theta square by 4. 4 cancels from 2 and 2, and you are ultimately left with v into theta, right? That is what is your dv vector, right? dv vector is nothing but v into theta. Now, you know that uh, what you are trying to find is basically acceleration vector, which is nothing but dv vector by dt, right? So this you can say, since V is a constant, so this is V theta d by dt, right? Now V is a constant. If you would have studied calculus, or even if you have not studied calculus, few things that would be studied in the, even before studying this circular motion, will be slightly slight discussion about what a differentiation is and all, when we are actually, when we are actually doing the course. But for the time being, you might already be aware that if it is dv theta by dt, then v comes outside, right? Because v is a constant. Here the magnitude of velocity is constant, so it comes out, and then it becomes d theta by dt. So acceleration is v d theta by dt, right? And d theta by dt, you already know, is given by omega. So it is v omega, right? Now what is v given as? It is given as omega r. We had just derived it. So omega r into omega, which makes it omega square r, right? So that is the value of acceleration that we are ultimately getting. Acceleration vector magnitude is coming out to be omega square r. And direction wise, you have already seen that the direction is inward towards the center, radially inward, right? So I think we have discussed pretty much now everything about the circular motion that is required to be known. Just summarizing here. So circular motion is a motion in a circle. First of all, we already know, we at any point, the uh, the velocity will be in the tangential direction, So your velocity will be pointing in this direction, v, right? At any point on the circle, velocity is going to be constant. The magnitude of the velocity is going to be constant, although its direction keeps on changing. At any point, it is tangent to that particular point. So the direction keeps on changing, but the magnitude of v remains same. And the magnitude of v is given by omega into r, where omega is the angular frequency with which the body is moving around this circle, angular speed with which this body is moving around in the circle, and r represents the radius of this circle. R is representative of the radius of this circle. So the velocity magnitude is omega into r. And also, we have studied that the direction of acceleration will be towards the center, So you can see that it will be always towards the center, trying to pull the body always towards the center, right? So that acceleration is going to act in the inward direction, and the magnitude of acceleration would be equal to omega square r, right? Omega square r. So these are certain things that we have studied in this chapter so far. So I hope we have made the important points we have understood. It was a valuable class for you, and you understood in depth about uniform circular motion. And if there are any doubts, definitely you can visit us at our website, give us a call, or write to us for any queries that you have. And very soon we are going to bring test series also to provide scholarship to our students, now if you want to join our classes. So hope you enjoyed the class, and keep up the good work. Try to solve the problems on your own, whether you are able to solve or not, but just give it a try. With the try and with understanding of the concept, slowly the things are going to improve, and you will be in a very better position, in a much better position to solve any problem, whether it's a simple one or a tough one. So with that, I would like to close this demo class for class 11. And for any queries, please get back to us, and we will be more than happy to help you out. So thank you. Signing off for now. Bye.